Hello guys, welcome to PLC Goods online video tutorial. In many control tasks, we need to control process time. For example, we might need to activate a motor or a pump for a specific time. In this video, we are going to explain the three most common types of timers, which are timer on delay, timer off delay, and retentive timer on delay. Then we will do a simple project with on and off delay timers. Let's start with this on delay timer, which it can be activated by this digital input. The timer consists of a timing block containing its name or address, which is T40, a time base variable which is set to 1 second. The preset value determines our desired time based on the time base variable. Right now, it is set to 10 seconds. Finally, the accumulator variable that contains the elapsed time. T40 is the timer address. In this format, T refers to a timer file. The number 4 identifies the file number. By default, file number 4 is used for timer instructions. The next number is 0, which refers to the first timer inside file number 4. It can be any number from 0 to 255. Each timer needs to store data such as the preset value and the status bits, so each timer consists of 3 words like these. The enable bit is true or 1 whenever the timer is enabled. The timer timing bit is set to 1 when the timer is in timing mode, and the done bit is turned on anytime the accumulated value is equal to or greater than the preset value. The first 13 bits 0 to 12, are reserved bits and do not do anything. Word 1 is used to store the preset value. Since it has 16 bits, it can be any number from 0 to 32,767. Now the time base variable is equal to 1 second, so the timer can be programmed for the maximum time of 32,767 seconds, which is about 9 hours. Now its value is 10. Let's see how a PLC stores its equivalent binary form in word 1. Word 2 is used to store the accumulated value. It can be any number from 0 to 32,767. When a timer starts running, this value will be increased by passing a time until it reaches the preset value. Let's see how an on-delay timer functions. As long as this contact is inactive, the timer is inactive as well, and the status bits, enable bit, timer, timing bit, and done bit are all false or 0. Now suppose this contact enables the timer. In that case, the enable bit is set to 1. Also, the timing bit will be on because the timer has started its timing mode, and the done bit will be off until the accumulated value reaches the preset value. Now the preset value is equal to 10 seconds. So, if the timer is disabled after 4 seconds, the done bit does not change to 1. Now let's activate the first digital input to enable the timer for a longer time. In consequence, a PLC sets the enable bit to 1. In this program, the preset value is 10 seconds. So as soon as the accumulated value becomes equal to the preset value, the timer stops timing and the done bit will be on. So we use a timer on delay timer when we need to start an action after a lapse of a certain amount of time. Now, to insert an on delay timer, click here to insert one. The inserted timer needs an address. You can select any timer inside the time file. Obviously, there is only one timer. We can have up to 256 timers. This is an advantage of using PLCs because we can have many timers without paying any extra money to have them. Let's select the first one and determine the time base and preset values. So according to the entered values, the selected delay for the timer is equal to 5 seconds. Now let's insert a normally open contact to enable it. Now I am going to use the status bits of the timer. Let's use the done bit of the timer. I can write the timer address and after that enter a slash, then write the desired bit name or a number. In the second line of my program, I want to use the done bit to turn on an output. Similarly, let's use the timer's timing bit to turn on another digital output. Now let's compile the program and transfer it to the PLC. Here I can either use my real PLC or use RSLogix Emulate 500 to create a virtual processor. Now let's use a virtual processor. My PLC is in program mode. Let's open RSLogix Emulate 500 and select the run mode. Let's enable the inserted timer with this contact. Obviously, in the beginning, the PLC turned on the timer timing bit and its connected output. And after 5 seconds, the PLC enables the done bit and its connected output. Let's use the PLC to download and test the program. My PLC is in run mode. I need to change it to program mode to transfer the program. Now click on yes to go to the online mode. When a computer is in online mode, the timer file can be opened to show time or the status bits. Obviously, PLC has activated the timer and based on the program, the first output is turned on, but my green lamp is off. Why? Because my processor is in program mode, I need to change it to run mode. Now let's enable the timer. Based on the program, the done bit of the timer will turn the green lamp on after 5 seconds. The PLC turned the lamp on with a delay of 5 seconds. If I change the time base to 0.01, this time will be 0.05 seconds. Note that the total delay is obtained using this formula. For instance, if I set the preset value to 1000, the PLC will turn the lamp on after 10 seconds because the time base value is set to 0.01 seconds. Alright, now let's create a flasher lamp with this timer. Let me insert a normally closed contact that refers to the done bit of the timer. I can select it from here or write its word and its bit number. In the beginning, the state of the done bit is false, so this contact remains closed. In consequence, I only need to enable the first digital input to enable the timer. After 10 seconds, the done bit is enabled. In consequence, the timer will be off for the next scan cycle. Again, the state of this contact is closed, and because I have not changed the state of the first digital input, the virtual power can reach the timer. As a result, the PLC will activate the timer for the next scan cycle automatically. So, in the first line of my program, I have a timer that is activated every 10 seconds automatically. Obviously, the accumulator word of the inserted timer includes the elapsed time. So, when the timer is running, each bit of this word is switching between 0 and 1 with a specific frequency. So, in the next line, I can use a bit of this word to create a flasher output. Now let me delete the third line and transfer the program to the PLC. Obviously, when I activate the timer, it runs continuously and I have a flasher output. Try to test this program with another bit of the accumulator word and test the result. Okay, let's learn about the two other common timers, timer off delay and retentive timer on delay. Their structures are similar to the on delay timer. Both use three words inside a timer file, have enable, timing, time, and done bits. So let me explain the difference between these two timers and the on delay timer. Notice that if we activate an on delay timer, the PLC turns on its done bit after a delay. But we can use an off delay timer to disable an output after a delay. Now this diagram illustrates how an on-delay timer functions. Note that I explained this diagram already. Now let me tell you its difference with a retentive timer on delay. For a retentive timer, if the first activation takes up 4 seconds, then for the next activation, the timer starts from 4 seconds, not from 0 seconds. So, a retentive timer keeps its previous time, and in its second activation, it needs only 6 seconds to reach the preset value. Note that if we disable this timer, it saves its previous time inside its accumulator word. So, we usually need to use a reset instruction to reset it. Inside RSLogix 500, next to the timer instructions, here is the reset instruction. We only need to define the timer address for the reset instruction. Let's see how to reset the first timer. Let's do a simple project. Develop a program to turn on an output when I0 push button is pressed and to turn it off when I1 input is activated. First, let's use an on-delay timer to turn on a horn for the first 5 seconds to warn that an oven will be turned on after a delay of 5 seconds. After the horn is stopped, a heating element coil is going to be turned on. Finally, after the oven is turned off, a fan continues to blow for 10 seconds. This is my program solution. I used two latch and unlatch instructions to save the start-stop requests on a bit of memory. I will use the first and the second digital inputs to start and stop the heater. I can use a bit of binary file to store Boolean results. We can easily increase the number of bits of the binary file if we need to. Let's use the first bit to store the start and stop requests. Now let's use this bit to activate an on-delay timer. Note that I also need an off-delay timer. So let's increase the number of timers inside the timer file. I use the first address for the inserted on-delay timer and the second one for an off-delay timer. Now let's add 3 rounds to my program to turn on the 3 outputs using the status bits of the inserted timers. The first output should be on only during the first 5 seconds after a start request, so I can use the timing time bit of the on-delay timer to turn on this output. Let's use the first digital output to control the horn. The second output, the heater, should be on after 5 seconds, so I can use the done bit of the on-delay timer for this output. Finally, the last output, the fan, should be turned off after 10 seconds, so let's use the done bit of the off-delay timer for this output. Now let's test this program with RSLogix Emulate 500. To start and stop the process, I have opened the input image table. Obviously, when I activate the first digital input, the horn is turned on immediately for 5 seconds and the heater will be turned on after 5 seconds. When I activate the stop input, the PLC turns off the heater immediately, but it turns off the fan after 10 seconds. Well, a counter might be used to count a number of revolutions of an encoder shaft, or perhaps the number of people passing through a door, and so on. Depending on a counter application, we have two types of counters: up counter and down counter. Usually, a reset instruction is used with counters. Finally, we will do a simple project in this video. Let's start with up counters. Counters are programmed like timers. A counter's name starts with the C letter, which refers to the counter file in a PLC memory. The next number, which here is 5, is the default file number of a counter file. But any unused file number from 10 to 255 can be entered here. A colon separates the file number from the counter number, which here is number 3. We can have up to 256 counters in each file number. Each counter element consists of 3 words. According to the program, the counting up bit, or CU, is on if the first input of the counter is activated. The next bit, CD, is used for done counters. The done bit is on when the accumulated value is equal to or greater than the preset value. Now, what is overflow bit? Pay attention. 32767 is the maximum number that can be stored with 16 bits. So anytime the accumulated count exceeds the upper limit of plus 32,767, the OV bit is set to 1 or true. The underflow bit UN is used for done counters. Other bits in word number 0 are reserved. The next word is used to store the preset value, and the last word is used to store the accumulated value. Note that we can use the reset instruction to reset an accumulated value of each counter to 0. Let's explain how this counter functions based on this diagram. According to the program, by the first digital input, we can send a pulse to the first input of the up counter to increase its value by 1 unit. Similarly, with the next positive edge signals, the accumulated value is increased until it reaches the preset value, which in this program is set to 4. When the accumulated value is equal to or greater than the preset value, the down bit will be on. Based on the second line, by activating this input, the counter will be reset and the accumulated value is changed to 0. Note that the overflow bit will be on if the accumulated value exceeds 32,767. Now we replace the up counter with a down counter to investigate the CD, DN, and UN bits and take a look at its counting timing chart. Obviously, the accumulated value is 6, which is greater than the preset value. So the done bit is activated at the beginning. We can use the first input to activate the CD bit, and in consequence, the accumulated value is decreased by 1 unit. Similarly, with the next positive edge signals, the accumulated value is decreased. Note that when the counter value is lower than the preset value, the down bit will be turned off. By using a reset instruction, we can reset the accumulated value to 0. Pay attention, at this time, the done counter is activated to decrease its accumulated value, and in the next line, the reset instruction can be used to reset the counter value to 0. So according to the priority, execution of second rung over the first one, a PLC resets the accumulated value to 0. Another point to remind is that the underflow bit is set to 1 when the accumulated value exceeds the lower limit of minus 32,768. Now let's insert and test the done counter. Here are up counter, down counter, and reset instructions. Let's add a done counter. Here I need to assign a counter name. Let's double click on a counter file. Here we can see the status bits, preset, and accumulated values of this counter. If we need 2 or more counters, we can click here to change this number accordingly. We can have up to 256 counters in each counter file. Let's use the fourth counter. The preset value can be a negative number such as -5. Let's use an input contact to activate the inserted counter. In the second line, I want to use a down bit to turn a digital output on or off. Now let's compile, save, and test the down counter with RSLogix Emulate 500. Here I use number 3 as the station number. RSLinks detected my virtual station, so let's download the program. Now let me open RSLinks Emulate 500 and change my virtual PLC's mode to run mode. The accumulated value is greater than the preset value, so the down bit is activated and my output is on as well. Let's decrease the accumulated value by creating a positive edge signal at the first input of the down counter. When the accumulated value is less than the preset value, the PLC turns off the done bit and in consequence, the output will be off. Now, let me change the accumulated value manually. Let's open the counter files to view the status bits. Let's activate the inserted down counter. As I mentioned before, when the accumulated value exceeds the lower limit, which is minus 32,768, the PLC sets the underflow bit to 1 and the next value of the accumulated word will be 32,767. See these two up and down counters which use the same addresses. I mean both of them are connected to C5-3 counter. The accumulated word has 16 bits. Its value can be changed within this range. Now its value is 4. First, let's use the up counter to increase the accumulated value. If its value exceeds 32,767, the overflow bit is set to 1 and the next value of the accumulated word will be minus 32,768. Similarly, if we use the down counter to decrease the accumulated value, when its value exceeds the lower limit of minus 32,768, then the underflow bit is set to 1 and the next value of the accumulated word will be 32,767. Now let's do a simple project. Consider this parking lot which has two indicators. We are going to develop a program to show whether the parking lot is full or not with two green and red lights. There is an inter sensor that is connected to an up counter which counts when a car enters the parking. Also, the exit sensor is connected to a down counter that its accumulator content value is decreased for 1 unit when a car exits the parking. Finally, consider an input to reset the counters. Okay, this is my program. In my program, the inter sensor is connected to an up counter which increases the accumulated value of this counter, C53. In the second line, the exit sensor decreases the accumulated value. Pay attention, the down counter is using the previous counter address C53. The third and fourth lines turn the two green and red lamps on or off based on the down bit of C53 counter. When the accumulated value is less than the preset value, the green lamp is turned on. Let's assume that the parking lot has a maximum capacity of 10 cars. When the accumulated value reaches 10, the red lamp is turned on and the green lamp is turned off. Finally, according to the last line, the operator can reset the accumulated value to 0. Let me test this program with the PLC. First, I have to make a connection between the PLC and RSLogix 500 using RSLinks. Now, let's download and test the program. The PLC is in program mode. Let's change it to run mode. Right now, the accumulated value of the inserted counter is 8. Let me reset that to 0. Now let's activate the inter sensor which is connected to the up counter. Obviously, the accumulated value is increased by each activation of the inter sensor. Similarly, the accumulated value is decreased by each activation of the exit sensor. Well, the accumulated value shows the current number of the cars parked in the parking lot. Based on the program, when the number of cars is less than 10, the green lamp is turned on. And when the red lamp is turned on, it means the parking lot is full. I hope you have learned how counters work and how they are used. Now, after a short introduction about integer and float data files, we will learn basic comparison instructions in PLC, and then I will explain what limit and mask instructions are. We learned how to work with output and input image memories whose file numbers are 0 and 1. We used a binary file to store some Boolean results on a PLC memory and learned how a timer or a counter works and how we can work with their status bits, preset or accumulated values. Similarly, we can use an integer file to store integer numbers like 3 or 16. We can increase usage number of this type of memory as well as the timer and counter files. In this data file, we can save a negative integer numbers too. The next data file can be used to store floating point or real numbers as well. Note that the address of integers start with N7 and the address of floating point numbers starts with F8. Naturally, I can save more than one floating point number. Note that we can also use this file to store negative real numbers. We can save integer numbers as real numbers. To do that, we only need to enter 0 as their fractional part. Now let's see what comparison instructions are. These instructions can be used to compare two numbers which are equal, not equal, less than, greater than, less than or equal, and greater than or equal. Let's learn how to use the greater than instruction. The greater than instruction output is true if the data specified as source A to be greater than the data specified as source B. In that case, this instruction can activate the first digital output. Source A can be any address of any data file which contains a value. For example, it can be the preset or accumulated values of a counter. Similarly, source B can be either a constant number or an address of a PLC memory which is used to store a number. I can change this address and use another address easily. Now the first number inside float data file with F80 address is compared with an integer number which is stored in the N72 address. Now let's use a constant number as source B. Let's test this simple program. I open this program in RSLogix Emulate 500 and define a suitable driver in RSLinks. Now let me download and simulate the program on my PC. The first value 2.9 is not greater than 10, so the output is off. Let me change the first value and see the result of the comparison instruction. Ten point one is greater than 10, so the simulator enables the output of the comparison instruction. Other comparison instructions like less than or equal and equal work similarly, except the limit test instruction. Let's insert a limit instruction to explain it with a simple test program. Let's enter 0 and 10 as the low and high limits. Now I want to enter a third integer number to test if its value is within the range or not. Let's test this simple program. The stored value on the N72 address is 16, which is higher than 10, so its value is not within the selected range and the output of the limit instruction will be off. Let's change the stored number on N72 address to 8. Obviously, the PLC turns on the output because 8 is between the selected low and high limits, which are 0 and 10. But this condition is not true for -2. Now we are going to see how mask comparison for equal instruction works. This instruction takes three numbers, for example 11, 10, and 30. You can see their binary form on the right side. Pay attention to the mask number. Its second and third bits are 1 in its binary form. So, this instruction compares the second and third bits of the numbers specified as the source and compare fields. In this case, the equality condition holds for these two bits, and in consequence, PLC turns the output on. Now suppose this bit is equal to 1. In this case, the three selected bits of the source and compare fields are not equal together, so the output will be off. Let's test this instruction in RSLogix 500. The stored numbers in these three addresses are equal to the three numbers which I used them in the previous slide to explain the mask comparison for equal instruction. Obviously, the output is on. Let's work with the binary form of the numbers. Pay attention to the mask number. The equality condition holds for these two selected bits. In consequence, the output is on. Now let's change this bit of the mask number. Now the equality condition is not true for the three selected bits. In consequence, the PLC turns off the output. Let's change this bit of the compare value. The three selected bits by the mask number are equal together and the output is on. In other words, if I use these three numbers as the source, mask, and compare fields, a PLC will enable the output of the mask comparison instruction. Let's improve this project which we did it in the previous video. Suppose there is an interrogate. We wish to open the interrogate if the parking lot is not full and the interrogate sensor is activated by a car. Let's modify the program a little more. The new program should open the interrogate when the parking lot is not full and the car has activated the interrogate sensor. A limit test instruction can be used to check the parking lot capacity. Let's use the interrogate sensor address for this contact inserted before the lim instructions. Note that I defined the symbol for this input already and I can write its symbol instead of entering its address. Let's write 0 and 10 as the desired low and high limits. Therefore, the interrogate can be opened if the accumulated value of my counter is within this range. Finally, let's use the third digital output to open the interrogate. Let's improve the program further by adding another condition to it. I want to use an off-delay timer for car's safety to ensure a car has passed through the entrance gate. Let's compile the program. Here is an error. This message invalid output instruction position appears because of the wrong number file. To resolve this error, I have to use the third digital output address and the off-delay timer output in two separate lines. So let's turn on or off the interrogate in the next line by the done bit of the off-delay timer. Now if the interrogate sensor is activated and number of parking cars is less than 10, the PLC opens the interrogate and when the interrogate sensor is deactivated, it closes the interrogate after 5 seconds. Let me compile, download and test the program. There isn't any error anymore in the program. I need to select the program mode. Let's select the run mode. Now let me activate the interrogate sensor. When the parking lot is not full, PLC opens the interrogate, and when a car is fully passed through the gate, it closes the interrogate after 5 seconds. Also, when the accumulated value of my counter reaches 10, the inter sensor does not open the interrogate. Now let's see what math instructions are, which can be divided into two groups. The first one is basic functions, such as addition and division. The second group is number system conversion. As an example, a TOD instruction converts an integer number to its BCD form. BCD is an abbreviation of binary coded decimal. Finally, we will do a simple project. OK, click on the Compute Math group. These are the basic functions: addition, subtraction, multiplication, division, square root, negate, and the three last instructions convert a number to its BCD form or its equivalent gray code. Let me explain the division instruction. First, I'm going to insert a wrong and a normally open contact. Now let's insert a division instruction. I use the first digital input address for this contact to enable the division instruction. This instruction takes two numbers and divides the first one by the second number. Then it stores the result in the address specified by the destination field or third address. This instruction can be used to store numbers in an integer or float data files. Let's test the instruction with three addresses of an integer data file, n7 integer. The division instruction calculates this mathematical formula. Let's change the initial values of the integer addresses. Based on these numbers, the formula's result is 5, and a PLC will store that in N72 address. Let me compile, save, and open the program in RSLogix Emulate 500 to test the program. Obviously, RSLinks has detected my virtual station, which I have created with RSLogix Emulate 500. I need to select the run mode for my processor. Obviously, the initial value of the third address is 0. When I activate the division instruction, its value changes to 5. Now let's change the second number to 3. Note that the exact result of division is 3.333, but my program's result is 3. Do you know why? Note that we used an address of the integer data file to store the result, which it can only be used to store the integer part of numbers, not their fractional part. To resolve this problem, I need to use an address memory of the float data file, which can be used to store real numbers. Let's download and test the new program. Let's select the run mode. Obviously, the program now calculates a correct result. Now, let's change the second number to 0. Note that in mathematics, division of a number by 0 is not defined. A PLC detects this as a fault and it switches to a stop mode automatically. Let's click on the status data file and on the Errors tab. Here we can see the detected errors and a short description of them, which can help us to know why a specific error has happened. Let's resolve this error. Note that the status data file shows us some information about the program, processor, scan times, and the errors that the PLC has detected. Obviously, right now, there isn't any error. The addition instruction adds two numbers together and stores the result in another address. The square instruction computes the square root of a positive number. The negate instruction changes the sign of numbers. Now let me explain the TOD instruction and the BCD standard. This instruction takes a number and converts that to its BCD form. Let's continue with a simple example. Here is an error. I cannot use a constant number for this instruction. So let's use an address of the integer data file. The error is resolved. Alright, the inserted instruction is activated. Obviously, the source and destination values are equal together. Both are 15. But what is their difference? If I open the integer data file, I see number 21 instead of 15. Let's look at the binary form of these numbers. This is the binary form of 15, but this is its BCD form of 15. In the BCD numbering system, a decimal number is separated into 4 bits for each decimal digit within a number. Let me explain the BCD code more. Consider number 62. This is its binary form. In this form, I cannot detect numbers 6 and 2. The BCD form is another standard to store numbers. This standard uses 4 bits to store each decimal digits within a number. The BCD standard is usually used to display numbers. In the current example, numbers 6 and 2 are stored separately, and I can send 62 to a 2 digits 7 segment display. I can design a simple BCD to 7 segment decoder, which has 4 inputs and 7 output lines. The output can be provided to a 7 segment LED display that shows a decimal number depending on the inputs. Similarly, I can use 2, 3, and more 7 segments to display higher decimal numbers. You have seen how TOD instruction converts a binary number to its BCD form. The FRD instruction works inversely. It converts a number from its BCD form to its binary form. At the end of the compute math group, the GCD instruction converts a number to its gray code. The gray code is another standard to store numbers. This table shows some standards to show numbers. Binary and hexadecimal standards for storing or representing numbers are very common in computer science. I explained the BCD standard as well. The main feature of the gray code is if we go from one decimal number to the next, only one bit of the gray code changes. Now I want to do a simple project. Let's start with the parking lot project, which its PLC program was generated in the previous video. Now let's assume that the parking lot has 2 interrogates. We need to use another up counter to add its value to the current value of the first up counter. Try to do this project on your own. That's simple. Now let me define and do another project. I want to convert a Celsius temperature to Fahrenheit. This is my program based on these conditions. First, suppose an analog input indicates a desired Celsius temperature. Let's assume it is equal to 60. I wish to develop a program to convert it to its equivalent Fahrenheit value. I use this formula to convert a temperature in Celsius to Fahrenheit. Based on the formula, the MUL instruction multiplies the temperature by 9 and stores the result in N70 address. Then the division instruction divides 5 into 540 and stores the result in N71 address. Then the add instruction adds 32 to the value of 108 and stores the result in N72 address. Finally, the PLC program converts the Fahrenheit value to its BCD form to show its value on a 3-digit 7-segment display. Let's test the program. Open the input data table. Let's change this analog input value. Assume this analog input value is equal to the Celsius temperature of a liquid. Now let me open the output data table. Obviously, the program result is 77. The PLC stored this number using the BCD standard in O0 address. Now, let's change the Celsius temperature. The program calculated its equivalent Fahrenheit value correctly, which it is equal to 126. Okay, we have reached the end of this video. I hope you enjoyed it. Thanks for watching this video.